In the quiet hours of the night, while consciousness fades and the body lies still, a complex symphony of biological activity continues to play out beneath the surface. For decades, we have viewed sleep primarily as a passive state of rest, a time for the body to simply recharge its batteries like a smartphone plugged into a wall. But in the mid-2020s, a paradigm shift occurred. We now know that sleep is not merely a pillar of health. It has become a diagnostic window, a crystal ball capable of predicting our future medical biography with startling accuracy. We have entered the era of sleep biomarkers. The convergence of artificial intelligence, advanced sensors, and big data has revealed that the architecture of our sleep, meaning the precise timing of our brainwaves, the variability of our heartbeats, and the microscopic twitches of our muscles, contains hidden codes. These codes are now being deciphered to predict the onset of neurodegenerative diseases, cardiovascular events, and metabolic disorders, years and sometimes decades before the first clinical symptom appears. Today on Fun Facts Online, we are going to explore this revolutionary science, tracing the journey of sleep biomarkers from the sterile environment of sleep labs to the smart devices on our wrists, and examining how nocturnal data is reshaping the future of preventative medicine. To understand this revolution, we must first redefine our subject. A biomarker, or biological marker, is a measurable indicator of the severity or presence of some disease state. We are all accustomed to standard biomarkers. You go to the doctor, they check your blood pressure for heart health, or your blood sugar for diabetes. A sleep biomarker is exactly the same concept, but it is a quantifiable characteristic of sleep physiology. Traditionally, sleep medicine focused on what we call macro-architecture. This asks questions like, how long did you sleep? How much REM, or rapid eye movement sleep, did you get? Did you stop breathing, which would indicate apnea? While these metrics remain important, the new frontier lies in the micro-architecture. These are subtle, often invisible patterns, buried deep within the raw data of sleep that a human eye might miss, but a computer never forgets. Current research divides these markers into two broad categories. First, we have physiological biomarkers. These are derived from clinical-grade equipment, primarily polysomnography, or PSG, which is the gold standard of sleep tracking involving wires attached to the head and body. These markers include specific brainwave oscillations, such as sleep spindles and K-complexes, as well as nocturnal blood pressure dipping patterns and precise muscle tone measurements. The second category is digital biomarkers. These are data points captured by the consumer technology many of us already own, such as wearables like smartwatches and rings, or nearables, which are devices placed near the bed that use radar. These track aggregate metrics like heart rate variability, the restless sleep index, and the sleep depth index. While these consumer devices are less granular than a clinical lab, their power lies in longitudinal data. A sleep lab watches you for one night. A digital biomarker tracks you every single night for years, creating a massive dataset that reveals trends over time. Perhaps the most profound application of these new sleep biomarkers is in the early detection of neurodegenerative diseases. Since the brain is the primary organ of sleep, it is arguably the first organ to show signs of distress when sleep patterns fracture. One of the strongest known predictors in all of medicine involves a condition called isolated REM sleep behavior disorder, or IRBD. To understand this, we have to look at how REM sleep works. Normally, during REM sleep, which is when we dream, the brainstem induces a state of atonia. This is essentially a safety lock, a temporary paralysis that prevents us from acting out our dreams. But in patients with IRBD, this safety lock is broken. They punch, kick, shout, and thrash in their sleep, often fighting off invisible attackers in vivid nightmares. Research solidified in 2024 and 2025 has confirmed that IRBD is not just a localized sleep disorder. It is actually a prodromal, or early, stage of synucleinopathies. These are diseases caused by the toxic accumulation of alpha-synuclein protein in the brain. The statistics here are sobering. Approximately 90% of men diagnosed with IRBD will eventually develop Parkinson's disease, dementia with Lewy bodies, or multiple system atrophy. Crucially, this sleep biomarker appears decades before the tremors or memory loss associated with these conditions. This provides a massive window of opportunity for medicine. Clinical trials testing drugs to halt Parkinson's are now specifically recruiting patients with IRBD, hoping to intervene years before significant brain damage ever occurs. While Parkinson's is linked to the REM phase of sleep, Alzheimer's disease is increasingly tied to deep sleep or slow-wave sleep. It is during this deep, restorative phase that the brain's glymphatic system kicks into high gear. You can think of the glymphatic system as a neurological dishwasher. It flushes out metabolic waste products that accumulate during the day, including beta-amyloid and tau proteins, which are the infamous hallmarks of Alzheimer's. New biomarkers, such as the sleep depth index, measure the integrity of this deep sleep. A fragmented or shallow deep sleep prevents the glymphatic system from performing its nightly cleanse. Longitudinal studies have shown that a decline in slow-wave activity in the frontal lobe of the brain can predict the accumulation of beta-amyloid years later. Thus, having a bad night's sleep is no longer just an annoyance. Over a timeline of years, it is a quantifiable risk factor that can be treated. The sheer volume of data generated during a single night of sleep is staggering. A standard polysomnogram records brain waves, eye movements, muscle activity, heart rhythm, and breathing simultaneously for 8 hours. For human doctors, analyzing this mountain of data point by point is impossible. They must rely on summary statistics. But for artificial intelligence, this data is a playground. In early 2026, researchers unveiled SleepFM, a foundation model trained on over 500,000 hours of sleep recordings. Unlike previous AI that was trained to look for one specific thing, like apnea, SleepFM was trained on the raw data itself, learning the fundamental language of sleep physiology. The results were groundbreaking. By analyzing a single night of sleep, the model could predict the risk of over 130 different health conditions with high accuracy. For cardiovascular health, it identified subtle variances in heart rate variability and beat-to-beat intervals that predicted heart failure and atrial fibrillation. For metabolic health, it found respiratory patterns linked to chronic kidney disease and diabetes. Perhaps most intriguingly, it could generate a sleep age for a patient. If your sleep age was significantly older than your chronological age, meaning your sleep architecture was degrading faster than it should, it was a potent predictor of all-cause mortality. The black box nature of AI means we don't always know exactly what the computer is seeing. It might be detecting micro-arousals, moments where the brain wakes up for a second, that are too short for a human to score, but, when accumulated over thousands of occurrences, signal immense stress on the cardiovascular system. While PSG and SleepFM represent the pinnacle of clinical accuracy, the revolution is being democratized by the device on your wrist. The market for wearables and nearables has matured from simple step counters to sophisticated medical devices. Modern devices now track a suite of digital biomarkers that serve as proxies for clinical health. One of the most important is heart rate variability, or HRV. This is a measure of the time variation between heartbeats. Contrary to what you might think, a very steady metronome-like heartbeat is not ideal. You want variability. High HRV indicates a resilient autonomic nervous system that can adapt to stress. Low HRV during sleep is a strong predictor of stress, inflammation, and impending illness. Another key metric is nocturnal dipping. In healthy individuals, blood pressure and heart rate should dip by 10 to 20% during sleep. People who are so-called non-dippers are at significantly higher risk for hypertension and stroke. Wearables are getting better at estimating this without the need for an inflatable cuff. Even respiratory rate stability is a powerful tool. Sudden changes in nightly breathing rates have been shown to predict COVID-19 infections and flu days before symptoms actually manifest. The regulatory landscape is shifting to accommodate this influx of data. The FDA and the European Medicines Agency are moving toward fit-for-purpose validation. This means a consumer device doesn't need to be perfect at everything. It just needs to be accurate enough for a specific claim. For example, major smartwatches have received clearance for detecting atrial fibrillation and sleep apnea history. However, a gap remains. Consumer devices are excellent at detecting sleep duration and circadian timing, meaning when you sleep, but they still struggle with accurate sleep staging. They often confuse quiet wakefulness, such as lying still in bed reading a book, with actual sleep, leading to skewed data. As with any powerful technology, the rise of sleep biomarkers brings unintended consequences. A new clinical phenomenon has emerged, called orthosomnia, derived from ortho meaning straight or correct. This describes patients who develop insomnia or anxiety specifically because of their sleep trackers. They become obsessed with their sleep score or readiness score. The irony is palpable. The anxiety about getting a bad sleep score releases cortisol, the stress hormone, which keeps the user awake, ensuring they get a bad sleep score. Clinicians are now seeing patients who sleep reasonably well subjectively, but are distressed because their device tells them they didn't get enough deep sleep. This highlights the need for emotional ergonomics, designing devices that inform users without inducing pathological performance anxiety. There is also the privacy frontier to consider. If your sleep data can predict your risk of Parkinson's or heart failure years in advance, who owns that prediction? Could a life insurance company deny you coverage because your sleep age is 5 years older than your actual age? Could an employer monitoring fatigue in truck drivers use sleep biomarkers to fire employees who are technically compliant with hours of service regulations but show biological fatigue? Currently, laws protect medical data, but consumer wellness data often falls into a gray area. As these biomarkers become more predictive, the data they are based on becomes more valuable and more dangerous if mishandled. Despite the challenges, the trajectory is clear. We are moving toward a future of preventative sleep medicine. Imagine a scenario in 2030. Your smart ring detects a subtle, month-long decline in your sleep depth index and a reduction in HRV. It doesn't just give you a score. It cross-references this with your genetic risk profile. The AI assistant on your phone alerts you, saying, "Your biomarkers suggest a high risk of cardiovascular strain. I've scheduled a proactive appointment with your cardiologist and adjusted your smart home thermostat to lower the bedroom temperature to optimize deep sleep." In this future, sleep is not just a passive activity. It is an active health monitor, a nightly checkup that happens without you lifting a finger. Sleep biomarkers represent one of the most exciting frontiers in modern healthcare. They transform the third of our lives we spend unconscious from a black hole of time into a rich source of biological insight. By listening to the whispers of our physiology in the night, we are learning to predict, and perhaps prevent, the storms of disease that await us in the day. From the terrifying clarity of Parkinson's predictions to the broad surveillance of AI foundation models, Nocturnal data is proving that while we sleep, our bodies are telling a story. The challenge now is to listen to that story responsibly, ensuring that this technology heals rather than harms, and that the promise of prediction leads to the reality of prevention.